In this problem, it tells us that we have carbon dioxide gas at 3 megapascals and 500 K, and that it's flowing steadily in a pipe at a rate of 0.4 kilomoles per second. And it says determine the volume of mass flow rates and density of carbon dioxide at this state. So we're determining the mass flow rate, which is m dot, the density, which is rho, and the volumetric flow rate, which is v dot. And it says if the carbon dioxide is cooled at constant pressure as it flows in the pipe, so that the temperature of carbon dioxide drops to 450 K at the exit of the pipe, determine the volumetric flow rate at the exit of the pipe. So let's draw a diagram. So we have the pipe, and we have CO2 flowing through the pipe. And it says that our pressure is 3 megapascals, and the temperature is 500 Kelvin. And it says that we have a molar flow rate of 0.4 kilomoles per second. And then for the second part of the problem, it says that the temperature here, so I'm going to put that this is T2, is 450 Kelvin. So the first thing we want to do is, so we're going to want to use, let's look at what we're solving for. So we're solving for the volumetric flow rate, and we're solving for the mass flow rate. So let's start with the volumetric flow rate. So we're given pressure, temperature, basically the number of moles, so the molar flow rate, and it wants us to find the volumetric flow rate. So we're going to use the ideal gas law to solve this. And we can use the ideal gas law because if we look up the critical temperature and pressure for CO2, the critical temperature is equal to 304.2 Kelvin, and the critical pressure is equal to 7.39 megapascals. So our temperature is above the critical temperature, and our pressure is below the critical pressure. So we can assume that this is an ideal gas. So the form of the ideal gas law that we want to use is PV, and we're dealing with volumetric. We're dealing with rates. So the volumetric flow rate is equal to the number of moles per second multiplied by the universal gas constant multiplied by time. So this is the form of the ideal gas law that we want to use, and the main reason is because this is given, and this is and the pressure and temperature are also given. So go over here to pressure. So these are all given, and we're looking for the volumetric flow rate. So let's solve this equation for the volumetric flow rate. The volumetric flow rate is equal to number of moles per second multiplied by the universal gas constant multiplied by temperature over pressure. So this is equal to 0.4 kilomoles per second multiplied by the universal gas constant, which is 8.314 kilopascals meters cubed kilomole K multiplied by the temperature, which is 500 Kelvin, and this is all over 3,000 kilopascals. So now let's cancel some units. The kilopascals cancel, kilomoles cancel, Kelvin cancels, so we're left with meters cubed per second. So this is equal to 0.554 meters cubed per second. So the volumetric flow rate is equal to 0.554 meters cubed per second. So now let's determine what the mass flow rate is. So to determine the mass flow rate, we want to use this form of the equation. So P multiplied by the volumetric flow rate is equal to the mass flow rate, and this is a big V. This is equal to the mass flow rate multiplied by the gas constant multiplied by temperature. So we want the mass flow rate. We know the volumetric flow rate because we just calculated it. We know the pressure and temperature because they were given. And we can look up R. We can either calculate R, so R is equal to the universal gas constant over the molar mass. So we can either calculate R or we can look it up. So R, and I'm going to write this over here with our other data. So R is equal to 0.1889 kilopascal meters cubed, whoops, this is lowercase m, meters cubed kilogram K. So let's solve this equation for the mass flow rate. The mass flow rate is equal to P multiplied by the volumetric flow rate divided by RT. This is equal to, the pressure is 3,000 kilopascals multiplied by 0.5543 meters cubed per second. So this is what we calculated up here. Divided by R, which is 0.1889 kilopascals meters cubed kilogram Kelvin multiplied by the temperature, which is 500 Kelvin. So now let's cancel some units. The kilopascals cancel, the meters cubed cancel, and Kelvin cancels, and we're left with kilograms per second, which is what we want. So this is equal to 17.6 kilograms per second. Now let's look at what else this wanted us to calculate. So it wanted us to also calculate the density. So the density, rho, is equal to the mass over the volume. So this is equal to m dot over v dot, which is what we just calculated. So m dot is 17.6 kilograms per second, and v dot is 0.554 meters cubed per second. So this is equal to 31.77 kilograms per meters cubed. Now let's do the second part of the problem. So the second part of the problem is asking us to calculate the volumetric flow rate at the exit, assuming that the temperature at the exit is 450 K. So it says the carbon dioxide is cooled at constant pressure as it flows in the pipe so that the temperature of the carbon dioxide drops to 450 at the exit. Determine the volumetric flow rate at the exit of the pipe. The pressure doesn't change, so the pressure here is still 3 megapascals. So let's go to the next, let's get a new page. So we want to use the same form of the ideal gas law that we used to calculate the volumetric flow rate initially. So this is PV is equal to the number of moles per second multiplied by the universal gas constant multiplied by temperature. So now we want to solve this equation for the volumetric flow rate, and everything else is known. So the volumetric flow rate, and I'm just going to specify that this is the exit, is equal to the number of moles per second multiplied by the universal gas law, universal gas constant multiplied by temperature divided by pressure. So this is equal to 0.4 kilomoles per second multiplied by 8.314 kilopascals meters cubed kilomole K multiplied by 450 Kelvin, and this is all over 3,000 kilopascals. Now let's go ahead and cancel some units. So the kilopascals cancel, the kilomoles cancel, and the Kelvin cancel. So we're left with meters cubed per second, and this is works out to 0.499 meters cubed per second.